Hello, welcome to the presentation of Team 5, Milli and the Volts, as we discuss our project, the Milli Locator, an energy harvesting dog tracking collar. Thank you for your interest in our project. Team members include me, Jordan Kaniainen, on the bottom right, Joel Gutierrez on the top left, Jennifer Harvell on the top right, and Kayla Richardson on the bottom left. All four of us are online students at Arizona State University. In addition to our electrical engineering experience, we also have experience in management, academic research, electrical trade work, and work in public utilities. This project was about utilizing energy harvesting to power a dog tracking device. Now, our research and customer discovery taught us that customers have an interest in such a device to be able to charge less often. And we have achieved this product by utilizing solar panels and an integrated circuit to trickle charge a lithium-ion battery. And the Milli Locator uses a GPS chip to receive position data from satellites, and a microcontroller unit, or MCU, then transmits this location data via Wi-Fi. And the locator also uses a buck-boost converter to regulate the voltage to ensure that a fixed 3.3 volts is delivered to the GPS and the MCU. The main purpose of this project and this device is to show that battery life could be extended through energy harvesting, showing that current is flowing from the solar panel to the battery to extend the life of that battery, to charge the battery. Team members will further discuss the details of this project and our results, beginning with Joel. Thank you.
Thanks, Jordan. I will now go over the original approach. The original approach for power management followed that which was presented in the EEE 488 proposal. Team members began by testing individual components before connecting them together on the breadboard. This included the batteries and the solar panels. So the batteries were tested first, and voltage and current were measured at the output using a 100 ohm resistor as a load. Next, the team then tested the solar panels with the same 100 ohm resistor. An open circuit voltage and load current were measured at the output of the harvesting system once everything was connected. And this allowed the team to verify that the LTC energy harvesting chip is capable of delivering power to an electrical load. I will now go over the results of the original approach. The team connected the solar panel to a battery pack to verify that the batteries are capable of being charged, and was able to charge a battery pack 0.73 volts in 2 hours under artificial light. So those were pretty good results considering they were under artificial light. Then the batteries were simply tested for voltage and current using a 100 ohm resistor. The results showed 3.77 volts and 35.85 milliamps for a setup of 3 AA batteries. The next test showed that the solar panels with the same 100 ohm resistor obtained 5.49 volts and 3.98 milliamps. So the two team members who were most successful in the LTC testing obtained the results listed in the table here in the chart. However, no team members were able to verify that the LTC chip allows for battery trickle charging using the solar energy. Kyla will speak next. Kyla.
Thank you, Joel. So since the majority of team members were not able to achieve the expected results from the LTC chip, we made the decision to develop a contingency plan for the energy harvesting system. The initial design included a solar panel for the harvesting component, a buck-boost converter to convert any input voltage to the required 3.3 volts for the load, and a battery which acts as the primary energy source. With this configuration shown, we were in fact able to verify that the battery was receiving a trickle charge from the solar panel. However, overcharge protection was still a concern. With this in mind, we did some research and we were able to find an integrated circuit configuration that was well suited for both our trickle charging and battery protection needs. This system consists of 3 chips, the first of which is the TP4056. This is a constant current, constant voltage linear charger for lithium-ion batteries. Next are the DW01A and FS8205A, both of which make up the protection portion of the configuration. The FS chip consists of 2 NMOS devices, one of which switches battery charging off if the battery voltage reaches 4.2 volts, and this is the maximum rated voltage for our primary battery. The other NMOS device switches battery discharge off when the battery voltage drops below 2.5 volts. This will allow the battery to be recharged by the solar panel without having to fall to 0 volts. The DW chip consists of detectors that compare cell voltage and signals if battery voltage is above 4.2 volts or below 2.5 volts, and this will allow the FS chip to operate as needed. After this configuration was assembled, current measurements were taken over the course of 1 hour to test the trickle charge capability of the system. Keeping the solar panel's voltage at a constant 3.6 volts, we measured a current of 0.12 milliamps traveling from the output of the charging IC into the battery. With this, we were once again able to verify the trickle charging capability of our system. Additionally, our most recent test results show that without the addition of the buck boost converter, the Milli Locator can operate between 7.5 hours to 8 hours depending on solar radiation. Once the battery voltage drops below 3.0 volts, however, the microcontroller unit can no longer operate and transmit our location data. Here, the buck boost converter is needed to step the voltage back up to 3.3 volts. Introducing the buck boost converter to the system in this way has resulted in an extra 1 hour and 12 minutes of successful operation. With the device fully operational, a user can view the Milli Locator's location data on their computer or mobile device via the Blink app. For GPS data transmission, we utilized an ESP8266 node MCU board paired with a U-Blox Neo 6M GPS module. The ESP receives location data from the GPS module and transmits that data to the Blink app through a Wi-Fi connection. Here we can see a demonstration of how the Blink app operates on a mobile device. Once the project is open, we can see latitude, longitude, speed, direction, and satellite information. We also have a map that shows a visual representation of the Milli Locator's location. Next, I will pass things along to Jen to talk about budget and conclusions.
Awesome. Thank you, Kayla. So during customer discovery, the team found that customers are willing to spend between $30 and $250 with an average of $109. And our final budget shown here corresponds to the system built using the alternative approach. Therefore, with the average sell price of $109 minus our cost of goods, our profit margin is nearly $68. However, that price does not include future work. So unfortunately, the team ran out of time to pursue the functionality of a power path, which would help extend battery life and protect the battery itself. This schematic created by the team shows our plan for such an idea. Other future work includes the obvious miniaturization of components, including a custom PCB that could be installed in a waterproof housing on the dog collar rather than the harness we used for this prototype. Additionally, we researched other technologies that could be considered for our next prototype. Due to time constraints and team competency, they were not used for the current Milli Locator, but thermoelectric generators, or TEGs, could be utilized for additional energy harvesting, and a LoRaWAN signal could replace the Wi-Fi capability for low-power, wide-area networking data communication of GPS coordinates. This brings me to the final slide, where Milli and the Volts would like to express the utmost thanks to our mentor, Dr. Keith Hulbert. They say a truly great mentor is hard to find, difficult to part with, and impossible to forget. Thanks also to Dr. Kazicki for the riveting lectures, And lastly, thanks to all the ASU faculty and students who joined us today. Maybe we'll see you on graduation day. Thanks again.